Det norske vitenskapsakademiet kunngjorde i mars at Abel-prisen for 2011 tildeles John Milnor. Prisen er på 6 millioner kroner og deles ut hvert år for fremragende vitenskapelig arbeid i matematikk.
Deres Majestet, statsråd, ærede gjester, kjære prisvinner, kjære venner. På vegne av det norske vitenskapsakademi har jeg gleden av å ønske dere alle velkommen til Abel-prisutdelingen for 2011. Prisen ble innstiftet ved 200-årsjubileet for Niels Henrik Abels fødsel i 1802. Det er 9. gang prisen til minne om hans innsats blir utdelt. Det er nok ikke tilfeldig når Abel-komiteens leder i sin begrunnelse for årets pris sier at, sitat, «Lik en inspirert musikkomponist som også er en karismatisk utøver, er årets prisvinner John Milnor både oppdager og formidler».
Abel-prisen for 2011 tildeles John Milnor for banebrytende oppdagelser innenfor topologi, geometri og algebra.
24. mai overrakte kong Harald Abel-prisen til prisvinneren under en høytidelig seremoni i den gamle losjen i Oslo. Professorene Christian Skau og Martin Rausen møtte prisvinneren til en samtale om hans arbeid med matematikk.
Professor John Milnor, on behalf of the Norwegian and Danish math societies, we want to congratulate you for being the Abel Prize laureate in 2011.
Thank you very much.
What kindled your interest in mathematics, and when did you discover that you had extraordinary aptitude for mathematics?
Well, I can place that quite clearly because the first time I really developed an interest particularly in mathematics was as a freshman at Princeton University. I had been a rather socially maladjusted, didn't have too many friends, and then when I came to Princeton, I found the mathematics common room was just an atmosphere at which I felt very much at home. People were chatting about mathematics, playing games. One could come in any time and relax, and then I found the lectures very interesting. And, I felt much more at home there than I ever had before, and I've sort of stayed with mathematics ever since.
You won or at least you landed on top of the Putnam
That's right, yes.
competition in mathematics.
Yes.
You were a Putnam Fellow in 1949 and 1950.
Sounds right.
So did you like solving math problems and puzzles?
Well, I think perhaps I've always approached mathematics that way as interesting puzzles to be solved, and so I certainly found that congenial.
Mm-hmm. Your first important paper was published in 1949, or at least was accepted in 1949 in the prestigious journal Annals of Mathematics, yes. And you were only 18 years of age at the time.
Yes.
And of course this is rather exceptional. The title of the paper was On the Total Curvature of Knots.
That's right.
Could you tell us about the idea? How you got the idea to that paper?
Well, I was taking a course in differential geometry. Al Tucker was the teacher, and he described the problem. There was a theorem, I believe, of Borsig, that if you have a closed curve in space and you take a measure of its total curvature, it's always at least 2 pi, and it is equal to 2 pi if and only if it's a round circle or a convex circle in the plane. And he said Borsig had Borsig is a famous Polish topologist who had posed the problem of asking what happened if the curve was knotted. What could one say about the curvature then? And I thought about it for a few days and came up with an answer. I think I did a very bad job of explaining the answer in the paper, but one has to learn how to explain mathematics. But that was very, very gratifying. In fact, someone else had produced a similar proof at about the same time, but still, it was a wonderful introduction to mathematics.
Oh, it's quite an achievement.
Yes.
Quite an achievement. When you started your studies at Princeton, was it in 1949 you started in Princeton?
Yes, that sounds right.
Then, of course,
Or
you met...
1948, perhaps.
Or maybe 1948. Well, anyway, you met John Nash
yes.
when you were in Princeton, and of course he was a PhD student, and
Yes.
3 years your senior, right?
Something like that,
Yeah,
yes.
right. And could you tell us, did you have any interaction with John Nash? I should tell, of course, that he is well known through the book, what is it called again? A Beautiful Mind, and
yes.
the film that was made. We want to hear your interaction with John Nash, and also how it was to be a Princeton student.
Well, as I've said, I spent a great deal of time in the common room. He also spent a great deal of time in the common room, so I naturally, he was a very interesting character. He was full of ideas, and he also went wandering around the corridor whistling things like Bach, which I had never really heard before, so it's a strange way to be introduced to classical music, but so I saw quite a bit of him over those years. He was also, I became interested in game theory around that time, which he, of course, was a very important contributor to, so what can I say? He was a very interesting person.
But I think you say that you played the Kriegspiel, Go, and also a game called Nash, right?
That's true, yes. Well, okay, Kriegspiel is a game of chess in which the two players are back to back, don't see each other's boards, and there's a referee who tells whether their moves are legal or not. And it's very easy for the referee to make a mistake. So it often happened that we couldn't finish because the referee got confused, and in that case we said the referee won the game. But it was a marvelous game. The game of Go was very popular there. My first professor, Ralph Fox, was an expert in Go, so I learned something of it from him and also from many other people who played. The game of Nash was, well, I think it was developed perhaps earlier in Denmark, but he invented it independently. It's also called Hex, and it's a very interesting game from a mathematical point of view, because it's a game where you can prove mathematically that the first player can always win, but there's no constructive proof. Nobody, and in fact, when you play, and it often happens that the first player doesn't win. So, but it's a very simple game mathematically based on topology.
You published some paper on games, and also with John Nash, right?
Yes, that's true. One paper was on a theoretical model for the game of Go, which has later been pushed further and developed by other people. Well, I suppose most successfully by John Conway. And there was also a paper on experimental games where we tried actually having a group of people play out a many-person game, and I think that experience convinced me that that many-person game theory was not just a subject of mathematics. It really involved social interactions and things far beyond mathematics, so I lost my enthusiasm for studying it mathematically.
You wrote your PhD thesis under the supervision of Ralph Fox.
That's true, yes.
And the title of your thesis was Isotopy of Links.
Yes.
Could you tell us, did you get the idea for this topic and what was the impact of this work later?
Well, certainly Fox was an expert in knot theory, so I learned a great deal about knots and links from him. And there were many people in the department then that were active, although it was other people in the department considered it a rather low-class subject and not really interesting. I think it's strange that although it wasn't considered a very central subject then, it's today a subject which is very much alive and very active. But as one example, there was a very quiet Greek gentleman, Christos Papakyriakopoulos, who was, I saw him around the common department, but or around the common room, but he was not very, I never really got to know him very well. I had no idea he was doing important work, but Fox had managed to find money to support him for many years, doing research more or less by himself, and he finally succeeded in solving a very important problem in knot theory, which was perhaps the beginning of a rebirth of study of three-dimensional manifolds as a serious part of mathematics. There had been a paper much earlier by Max Dane in which he proved a simple property about knots, essentially that I can just state it in mathematical terms, if the fundamental group of the complement of a knot is cyclic, then the knot, it can be unknotted. And this proof by Max Dane had been accepted for at least 20 years until someone pointed out that there was a big gap. So after this was then for many years a famous unsolved problem, a problem of Dane's lemma, a statement which he'd made that he'd given a false proof of and that yet seemed to be true. And nobody had made any real progress with it until Papakyriakopoulos developed completely new methods and managed to give a proof and of other related theorems. So that was a big step in mathematics and an example of a case in which somebody working in isolation by himself has made a tremendous progress. There are relatively few examples of that. There are some other famous ones, the Andrew Wiles and the solution of the Fermat's problem, again, was somebody who was working by himself and surprised everyone when he came up with a proof. And another example is Grisha Perelman in Russia, who was working very much by himself and produced a proof of the Poincare hypothesis. But these are isolated examples. Usually mathematicians work in a much more social context, communicating ideas to each other, and ideas travel from country to country very rapidly. We're very fortunate in that mathematics is usually totally divorced from political situations, so that even in the height of the Cold War, we received information from the Soviet Union, and of course the people in the Soviet Union were eagerly reading papers from outside, so mathematics was much more open than most scientific subjects.
As a footnote to what you say before I leave Martin ask you questions, Max Dane was of course was an important person. He was a student of David Hilbert and he proved Hilbert's third problem.
Yes.
Which about the polyhedrons, you know, how you
Yes.
cannot compare them. So no wonder that people trusted his proof, maybe because of his name.
Yes.
Yeah.
Well, it's a cautionary tale, because we tend to believe in mathematics that once something is proved, it stays proved. And cases like this, where a false proof is accepted for many years, are very rare.
Right. Okay.
Okay. So coming back to your own achievements. For several years after your PhD work, you mainly concentrated your research on the theory of manifolds.
Yes.
So could you, to start with, explain us what a manifold is and why manifolds are important?
Well, in low dimensions, manifolds are things that are easily visualized. A curve in space would be an example of a manifold, or a surface, the surface of a sphere or a donut, or two-dimensional manifolds. But for mathematicians, the dimensions 1 and 2 are just the beginning, and things get more interesting in higher dimensions. And also, for physicists, the manifolds are very important, and it's essential for them to look at higher dimensional things. For example, suppose you're studying the motion of an airplane. Then, first of all, if you just want to describe the position of the airplane, it takes 3 coordinates. But then you want to describe what direction it's going in, what is the angle of its wings, and so on. So it takes 3 more coordinates to describe the well, just to describe the position, it takes 3 coordinates for the point in space where the airplane is centered, and 3 more coordinates to describe its orientation. So you're already in a 6-dimensional space, and then you have a path in a 6-dimensional space. And this is just the beginning. If you're studying the motion of particles in a gas, then you think of some enormous number of particles bouncing around. Each one has 3 coordinates to describe its position, 3 coordinates to describe its velocity, and so if there are 1,000 particles, you're already up to 3,000 dimensional space, and then a motion in it, the velocity takes another 3,000 coordinates, and of course much larger numbers occur. So mathematicians and physicists are very used to working in large dimensional spaces.
The one result that made you quite immediately famous at age 25, I believe, was the discovery of different exotic structures on the 7-dimensional sphere. So these are smooth manifolds that are topologically equivalent to a 7-dimensional sphere, but not in a smooth in a differentiable sense. Could you explain this result a little bit, and also describe to us how you came up with the ideas?
Well, I certainly came up with it by accident, and was very startled by it. I had been working on a project of understanding different kinds of manifolds from a topological point of view, and in particular I was looking at some examples of 7-dimensional manifolds which were constructed by a simple, well-understood construction. They were very explicit, smooth objects, which I would have thought were well understood. But then looking at them from 2 different points of view, I seemed to find a contradiction in mathematics. One argument showed that these groups were spheres, topologically spheres. And another very different argument showed that they couldn't be spheres. And well, mathematicians get very unhappy when they have good proofs of 2 contradictory results. It's something one doesn't like to have. And the only way I could get out of this dilemma was by assuming that there was a big difference between the concept of a topological sphere and the concept of a differentiable sphere, something which is smoothly homeomorphic to the standard sphere. So this was something which hadn't been expected. I'm not aware that anybody had specifically asked the question. We just assumed that the answer was obvious, that for some purposes one assumed just a topology, for other purposes one assumed a differentiable structure, but nobody had really considered the possibility that there was an essential difference between them. So this This awakened a great deal of interest and a need for further research to understand exactly what was going on.
And you were certainly the driving motor in this research and applied both techniques from differential geometry topology and also algebraic topology to shed new light on this area. And I think it's probably fair to say that work of French mathematicians, European mathematicians, maybe in particular French mathematicians like Thom and Jean-Pierre Serre, who, by the way, got the first Abel Prize here in Oslo 8 years ago, they made very fundamental contributions that made your approaches possible.
Yeah.
And how did collaboration work over the Atlantic at the time?
Well, it was very easy to travel back and forth, and I found French mathematicians very welcoming. I spent a great deal of time at IHES near Paris. So I never had very much contact with Serre, but I admired him tremendously, or still admire him tremendously, and his work has been an enormous influence. Thom I got to know much better. He was really marvelous. He had an amazing ability to combine geometric arguments with hard algebraic topology and come up with very surprising conclusions. So I was a great admirer of Thom, and found he also was extremely friendly.
And then building on the work of, amongst others, Frank Adams from Britain and Stephen Smale from the United States, you were able to complete, to a certain extent at least, the classification of exotic structures on spheres together with Michel Calvert from France again.
Yes.
And well, there are still some questions in the stable homotopy of spheres that are open.
Yes.
But at least up to those, we know what is able to, or what one can ask about on structures on spheres, right?
That's completely true, except in dimension 4.
Yes.
Yes, there are very classical arguments which work in dimension 1 and 2. Dimension 3 is already much more difficult, but the work of first Bill Thurston and then Grisha Perelman has more or less solved that problem. And it was a tremendous surprise when we found in the 60s that high dimensions were easier than low dimensions, that once when you get in a high enough dimension, you have enough room to move around so that arguments become much simpler, and with some work one could push things down to dimension 5, but dimension 4 is something else again and very difficult. Neither methods work.
And one seems to need much more hard, pure analysis to work in these dimensions, right?
Well, yes and no. Michael Friedman first proved the topological Poincare hypothesis in dimension 4, and that was the very opposite of analysis. It was completely methods of using very wild topological structures with no differentiability. But the real breakthrough in understanding differentiable manifolds came not from mathematicians, but from mathematical physicists, where methods of gauge theory and later the Seiberg-Witten work, which was motivated by pure mathematical physics, but turned out to be enormously useful in pure mathematics.
When we look at terminology in manifold theory, then it's quite pictorial and often down to earth. So some techniques are known as plumbing, and surgery has become a real industry in mathematics.
Yes.
And you have written a paper on killing,
yes.
Of course, just homotopy groups.
Yes.
May I ask to what extent this terminology is, to what extent you are responsible for this terminology?
I may have introduced the term surgery, which just cutting up manifolds and putting them together in a different way. The word term spherical modification is also used for the same thing. There's much later, the idea of quasi-conformal surgery has played an important role in holomorphic dynamics. Well, simple graphic terminology can be very useful. There's some words that just get used so much that one loses track of what they mean, and they may change their meaning over the years. So things like regular or smooth are very dangerous. So there are so many important concepts in mathematics. It's important to have terminology which makes it clear what you're talking about. Use of proper names can be very useful because there are so many more proper names, and if you have the right proper name attached to a concept, it really pins it down better than using everyday words like jet and but it takes a combination of good terminology is very important, and can have a very good influence if it's successfully used, and can be very confusing if it's badly used.
A surprising result from your hand was a counterexample to the so-called Hauptvermutung, the main conjecture, dating back to German mathematicians in combinatorial topology, and it has to do with triangulated manifolds, or more general triangulated spaces. Could you explain what you proved at the time?
Well, let's see. One of the important developments in topology in the early part of the 20th century was concept of homology and later cohomology. In some form they'd been introduced already in the 19th century, but it was a real problem to make sense of them. So one of the first attempts to make sense of them was to start by cutting a topological space up into simplexes, up into linear pieces, rectilinear pieces, and then you could easily prove that homology was well defined on that level, and that well behaved if you cut simplexes up into smaller ones. And then a natural conjecture was that you were really doing topology when you did this, so that if two simplicial complexes were homeomorphic to each other, then you could cut them up into pieces which corresponded to each other. So this was the first attempt to prove that homology was a topological invariant. Well, nobody could quite make it work, so they developed better methods and got around the problem. But the old problem of the Hauptvermutung, assuming that you always could make such a subdivision, remained open. And I ran into an example where you could prove that it didn't work. This was a rather pathological example of things were not manifolds, but much later, people, or 10 years later, maybe, I've forgotten, people found that you could also give counterexamples for manifolds. A number of people worked on this, but the ones who finally built a really satisfactory theory were Rob Kirby and my student, Larry Siebenman.
You know, mathematics traditionally is divided into algebra analysis and geometry topology. And of course it's fair to say that your most spectacular results has been in geometry topology. Could you say something about your working style and intuition? Do you think geometrically, so to say, and visualization is important?
Very important, yes. Yes, I definitely have a visual mind, so that it's very hard for me to carry on a mathematical conversation without seeing anything written down.
But on the other hand, it seems to be a general feature that, at least when you go into a higher dimensional topology, real understanding comes when you find a suitable algebraic mirror image that allows you to formulate what you...
Well, you also often just think by analogy, so that you can have pictures in small dimensions and you sort of know how much of the picture remains accurate in higher dimensions and how much has to change. It's very different from writing down a string of symbols.
But certainly you have also worked very hard on algebraic aspects of topology and also algebraic questions in their own. I mean, in the development of manifold theory, there are in the same time you have papers on Steenrod algebras, on Hopf algebras, and so on. So at least it seems to me that you also have a very algebraic mind at the same time.
Well, one thing leads to another. If you have a purely topological problem and the answer requires algebra, you're forced to learn some algebra. So as an example, a study of manifolds involved one of the essential invariants, first studied by Henry Whitehead, was a quadratic form of a four-dimensional manifold, or 4K dimensional manifold more generally. And so trying to understand this, I had to look up the research on quadratic forms, and I found this very difficult until I found a beautiful exposition by Jean-Pierre Serre, which provided exactly what I needed to know. And well, I discovered that the theory of quadratic forms is an exciting field on its own. So I just sort of rather following my nose, doing what came next, I started studying properties of quadratic forms, and about this, in these years also the K-theory developed, for example, by Michael Atiyah was a very exciting development, and there were beginnings of algebraic analogs. Well, perhaps Grothendieck was one of the first. Hyman Bass developed a theory of algebraic K-theory, and I pursued that a bit further. And then I discovered that there were relations between the theory of quadratic forms and algebraic K-theory. John Tate was very useful at that point, helping me work out how these things corresponded. I think I made a very lucky guess at that point at conjecturing a relationship between algebraic K-theory, quadratic forms, Galois cohomology, which I had really very little evidence for, but it turned out to be true and was much later proved by Voevodsky. So that was, well, I mean, it's very easy to make guesses, but it feels very good when they turn out to be correct.
Well, that's only one of the quite famous Milnor conjectures.
Well, I've also had conjectures which turned out to be false. So
but always very instrumental, I believe. So algebraic K-theory, that was another topic that you already mentioned. And if I might guess, then probably your interest came in through Whitehead groups and Whitehead torsion K1.
Yes, that's certainly true.
Yes, and that is quite obvious that this is instrumental in the theory of non-simply connected manifolds and through the Escobar-Corbordsen theorem and so on. But that must have thrilled your interest in general algebraic K-theory, where you have a version of which is called Milnor K-theory these days, and Dan Quillen then had a competing or a different version, building maybe a bit more topological underpinning of that.
Well, certainly in topological K-theory, it worked in all dimensions. It had a periodicity property, so it was fairly straightforward. It seemed there should be a corresponding algebraic theory, and well, Bass had worked out a very complete exposition of K0 and K1, and I managed to find an analog of K2, which is completely identical with the Quillen theory for K2. I mean, the motivation and exposition were different, but I mean the mathematical objects were the same. I had no real idea of how to go further. Quillen developed a complete K-theory for all dimensions, but I just made a rather ad hoc definition for higher dimensions, which, well, in no sense is it a substitute for the Quillen K-theory. It's not the same, but it turned out to be very useful for a certain kind of problem, so it has kept a separate identity.
Motivic cohomology and developments in that direction, right? And
You introduced the concept of growth function for a finitely presented group in a paper from 1968, I think it was. And then you proved that the fundamental group of a negatively curved Riemann manifold has exponential growth. And this we sort of read in the literature that paved the way for a spectacular development of the modern geometric group theory, and eventually led to Gromov's hyperbolic group theory. And of course, Gromov got the Abel Prize 2 years ago. Could you explain to or tell us why you found this concept so important?
Well, I'd been very much interested just in the relations between the topology of the manifold and the geometry of the manifold. So there were some classical theorems that were well known. For example, Priceman had proved that if you have a manifold of strictly negative curvature, then any abelian subgroup of the fundamental group must be cyclic. But this seemed to be a way of just a simple property of groups which would reflect reflect the geometry in the fundamental group. I wasn't the first to do this. Schwartz in Russia had done very similar work before me, but perhaps I was better known and got much more publicity for the concept. Now let's see. Well, I can bring in another former Abel Prize winner, Jacques Tits, had proved what's called the Tits alternative for finitely generated subgroups of algebraic groups. He proved that either there was a free subgroup or the group was solvable. And all the groups that I was able to construct had this property. Either the group contained a free subgroup, a non-trivial free subgroup, or else it was essentially a solvable group. So this remained this problem of groups of intermediate growth remained an unsolved problem for many years until Grigorchuk in Russia found an example showing that you could have groups which were in between, which had less than polynomial growth, but more than less than exponential growth, but more than polynomial growth. So, well, it's very nice to ask interesting questions and find that people have interesting answers.
Well, we have to get over the last 30 years or so, you have worked quite extensively on the real and complex dynamics. Where one studies, roughly speaking, iterates of a continuous or holomorphic functions and the associated orbits and stability behavior. We are very interested to hear why you got interested in this area of mathematics.
Well, I first got interested under the influence of Bill Thurston, who himself got interested from actually problems in mathematical ecology. So there was, I'm sorry, I have a very bad memory for names, but there was a theory. You considered the following situation. Suppose you have say, an isolated population of insects which can either grow or reduce, and if there get to be too many of the insects in this area, they use up the resources and start to die off. But if there are too few, then they can grow exponentially. So you have a kind of a curve where if the population is very small, it tends to rise, and if it gets too big, it tends to fall down again. And this led to the mathematical study of properties of this kind of function. What happens when you look at one year after another, you get a very chaotic looking set of population data. So Bill Thurston had gotten very interested in this problem and explained some of his ideas to me, and as frequently happened, I first was very dubious.
Yeah, and this paper was a seminal paper, and I know that the dates of the paper was around 1977, and the manuscript circulated for many years before it was published in Springer Lecture Notes in 1988. And there you introduce a new basic invariant that we call the Kneading matrix and the associated Kneading determinant. And you prove a marvelous theorem connecting the Kneading determinant with the zeta function for the map, which the zeta function, of course, is associated to periodic orbits, etc. And please tell us, I read part of this paper, and it seems like this is a delight to write the paper. It really seems that your enthusiasm sort of shows through the reading.
Yes. Well, you said that the zeta function, of course, describes periodic orbits, which is true, but it omits a great deal of history. Of course, zeta functions were, well, first made famous by Riemann, and looking at the Riemann zeta function, which actually had, I think, been studied earlier by Euler. But so that was so the zeta functions were first important in number theory, but then people studying dynamics found that the same mathematical formalism was very useful for counting periodic orbits. I suppose the catalyst was André Weil, who studied the analog of the Riemann zeta function for curves over a finite field, and he found that it was closely related to periodic orbits of the Frobenius involution. So that there's a continuous history here from pure number theory, starting with Euler and Riemann and André Weil, and then to problems in dynamics in which one is just studying iterated mapping and counting how many periodic orbits it has. So it's well, this is typical of what makes mathematicians very happy, when techniques which are invented in one subject turn out to be useful in a completely different subject.
But you must have been surprised after all studying continuous map of interval into itself, leading to such deep results.
Well, it was certainly a very enjoyable subject.
The work that with Thurston has been compared with Poincaré's work on circle diffeomorphisms 100 years earlier, which inaugurated the qualitative theory of dynamical systems. Mm-hmm. So it had a tremendous impact on the subject. That's certainly what, just checking the literature, it's easy to see that. Well, this leads actually to another question. I mean, there is a journal called Experimental Mathematics, yes, and the first volume came in 1992, and the first article was written by you on the some cubic polynomial iterates of that. And of course, a lot of the pictures, using the computers. Yes. What's your view on computers in mathematics? I mean, based on, and you wrote several papers actually in experimental mathematics.
Yes. Well, I guess I was fascinated by computers from the very beginning, and at first one had to make these horrible punch cards and feed things into a computer. It was a great pain, and it's gotten easier and easier. And I'm afraid the biggest impact of computers in mathematics has been just making it easier to prepare manuscripts. I always have had a habit of rewriting and editing, and so in the early days I drove the poor secretaries crazy. I would hand in these messy longhand manuscripts that would present a beautiful typescript, and then I would cross out this, change that, add this, and well, it was very hard on them. So it's been so much easier since computers have made it easy to edit manuscripts. But well, the other point is that it makes it easier to carry out numerical experiments now. these are nothing new. Gauss made a great deal, carried out a great deal of numerical experiments, but of course it was very painstaking in his time. And it's gotten so much easier. So in particular, if you have a dynamical system which is very hard to prove anything definite about, it's very helpful just make a simplified model that you can run on a computer and hopefully get an accurate result. But it's very dangerous also, because you never know when the round-off errors by the computer or computing error has produced a result which is not at all accurate. So it becomes a kind of art, understanding what the computer can do and what it can do, what the limitations are. But it's enormously helpful. So you can get a fast idea of what to expect of a dynamical system, and then try to prove something about it using the computer results as an indication of what to expect. Or at least that's in the best case. There's also the other case where all you can do is obtain the computer results and hope for the best that that's accurate.
So in that sense, this mathematical discipline at least resembles a little bit more what physicists do when they plan their experiments, and then from the experiments try to get results.
Well, then there is the intermediate stage of computer-assisted proof, where at least if you believe there are no mistakes in the computer program, you have and no mistakes in the hardware, you have a complete proof. But of course, this assumption that there are no mistakes is a very important one. I know Enrico Bombieri had an experience, was using some fancy new high-speed computer to make experiments in number theory, and he found that in some cases the results just seemed wrong. And he traced it back and finally found that there was a hardware mistake in the computer.
No. You have written some textbooks which are legendary in the sense that they are lucid and lead the readers quickly to the point, seemingly in the shortest possible way. And the topics of your books are within differential topology, algebraic K-theory, characteristic classes, quadratic forms, and holomorphic dynamics. Your books are certainly enjoyable reading, but you do get to the point very, very quickly and in a very, very elegant way. Do you have a particular philosophy when you're writing mathematical textbooks?
Well, I think most textbooks have arisen because I was trying to understand a subject, and I mentioned before I have a very visual memory. The only way I can be convinced that I understand something is to write it down, and to write it down so that I can understand it. So I think the clarity of writing to the extent that it exists is because I'm a slow learner and have to write down many details to make sure I'm right.
Two questions come to mind. Do you enjoy writing articles of a historical survey type? You certainly have an knack for it. And do you think it is important that articles and books on mathematics of a popular and general nature are written by prominent mathematicians like yourself?
I mean, mathematics has such a rich and interesting history, and it's very hard to keep track of because terminology changes. I mean, you read an article written 100 years ago where they describe a function as being regular, and it's very hard to find out what they meant by that. So it's important to have definitions which are clearly written down, so even if the terminology does change, people can understand what you are saying.
And you're interested in the history of mathematics also? Follow how ideas develop?
Well, I mean, history to a scientist is usually the history of ideas that work. One tends to be rather bored by ideas that didn't work, whereas to a true historian would be interesting in how the ideas developed and the false leads also. So I think the kind of history that I would write is very biased. It's trying to find out where the important ideas we have today, where they came from, who first discovered them. So I find that a fascinating field.
Could we ask you, are there any mathematicians that you have met personally during your lifetime that have made a special deep impression on you?
Well, are there any? There are many, of course. I think the one, I mean, there were certainly the professors at Princeton, like Ralph Fox, Norman Steenrod, Emil Artin, made a very strong impression on me. Henry Whitehead was, remember he invited a group of very young topologists to Oxford, which is a wonderful experience for me when I was young. I've mentioned René Thom. More recently, Adrien Duhady was a very important influence. He was an amazing person, always full of life, always willing to talk about any mathematical subject.
A question in a different direction. You have many results that are described as a breakthrough in, by mathematicians all around. When I ask you about memorizing several of the instances when an idea struck you, and now a result has emerged, would you say that it rather occurs when you have been working on it and worked on it very intensely, or did it often happen in a more relaxed atmosphere where you maybe not were speculating about it very, very directly? Is there a common answer to this question?
Well, I mean, certainly one scenario is that one worries and studies about a question. One night you go to sleep wondering what the answer is, and when you wake up in the morning, you know the answer is. But the other possibility is that you're just sitting at a desk working and finally something works out. There are all possibilities, or that a conversation with someone, you combining, certainly communication is very important in mathematics. Talking to people, reading other people's work, talking to them, getting suggestions is a very essential process.
When we look at mathematics as a whole, it has also changed during the years that you have been through.
Yes.
And one question could be well, mathematics has some periods where there is more space for internal development. And then there are other periods where, well, momentum comes more from other disciplines, like physics in the past, certainly. Mm-hmm. So when we look at our times, what period are we in? What influences from the outside would you say are very important now? And maybe if you venture to look into the future, how will that develop?
Well, I think the big mystery is how the relation between biology and mathematics. That is that
You've mentioned ecology as one example.
Yes.
Mm-hmm.
Well, that's making a very simplified mathematical model. It's clear that biological problems are so complex that you can never make a total mathematical model. But it's part of the general problem of applied mathematics. Most things that occur in the real world are very complicated. The art is to realize what are the essential variables, what are the essential properties, and to try to, if you can find a simplified model that really says something about the real, more complex situation. Now, there's been a tremendous success in just understanding large sets of data, statistical analysis, which is, well, it's certainly not the kind of mathematics I've ever done, but it is a kind of mathematics, and it's very important. But
in an article 10, 15 years ago, you described several areas of mathematics that you had at first judged as being of minor interest, and then later on turned out that they were fundamental to solve problems that you had been working on yourself. Yes. I think Friedman was one of the examples you mentioned in Friedman's work.
Yes.
Can you give maybe another example and then a moral also from this point of view?
It's certain. I mean, I think one of the joys of mathematics is that it doesn't take an enormous grant and an enormous machine to carry it out. One person working alone can still make a big contribution. And there are so many possible approaches to questions. I think it's a big mistake to have everything concentrated in a few areas. The idea of having many people working independently is actually very useful, because it may be that the good idea comes from a totally unexpected direction. It's happened so often.
It leads to a natural question, and this is of course in a way impossible to answer, I guess, but what is mathematics to you? What is the best part of being a mathematician?
Trying to understand things, trying to explain them to yourself and to others, interchange. So watching how other people deal with and develop new ideas. There's so much going on that no one person can understand all of it, but you can admire other results even if you don't follow them in detail. I just find it's a very exciting world to be in.
So having talked about mathematics all the time, can we close up by asking about what other things you are very interested in, your hobbies, your private interests in your spare time?
I suppose I like to relax by reading science fiction or other silly novels. I certainly used to love mountain climbing, although I was never an expert, just someone who enjoyed doing it. I've enjoyed skiing again. Although I was never an expert, but again, it's something I enjoyed doing. I hope I'll be able to take up skiing again. I didn't manage it this winter.
So coming to an end, we would like to thank you very much for this most interesting interview. And this is, of course, on behalf of the two of us, but also on behalf of the Danish Mathematical Society, the Norwegian Mathematical Society, and also the European Mathematical Society. Thanks a lot.
Thank you very much. Thank you.
I've been warned